Salam to all. What is amyloidosis? What is its definition? Its physical nature? What is its chemical and biochemical composition? I am the Professor Ghalia Khalaf, nephrologist at Mohamed Lamine Debarine Hospital in Algiers, who will try in this video to answer these questions. We will start by coding my presentation plan. Definition, into history, physical nature, light microscopy, amyloidosis fibrogenesis, favoring factor for amyloid fibrogenesis, and we will finish by nomenclature in this first presentation. Amyloidosis refers to a variety of conditions in which amyloid proteins are deposited abnormally in the extracellular environment between the cells of various organs and tissues. Amyloidosis is a protein whose secondary structure is altered, giving it a particular insoluble form. This shows an anatomopathologist who will use Lugol. This solution is used as an indicator of the presence of starch in organic compounds, with which it reacts turning dark blue or black with starch, due to the interaction of iodine with the helical structure of polysaccharide that contains in organs and tissue extirper of sick patients who have been autopsied. Then we give this name of this structure for the name of amyloid, derived from the Greek words amylon or amylum in Latin, meaning cellulose or starch. We're going to speak about different findings in amyloid protein, or in how we are discovering novel proteins, how we are show this protein and giving names of all these protein. Nicolas Fontanis in 1639, first description of amyloid white spleen. In 1838, Matthias Shandon coined the first term of amyloid. In 1842, Rokitansky described for the first time. Virchow defines amyloid. 1859, Friedrich and Kickel discover a protein in amyloid deposit. 1927, birefringence reinforced by Congo red amyloid is structured. 1936, Bill Astbury took the first diffraction images of fibers and discovered the existence of a fibrous state for many proteins. 1959, Cohen and Calkins show section of electronic microscopy tissue containing fiber by 6 and 13 nanometer wide. 1967, Shurama and Cohen defined amyloid as being composed of twisted protofilaments. 1968, method of extraction of amyloid with water. 1971, cross-fiber diffraction pattern sequencing revealed that specific proteins are involved in AL amyloidosis. 1978, identification of transthyretin, precursor protein of familial amyloid polyneuropathy. 1985, cross-fiber diffraction pattern that specific proteins are involved in AL amyloidosis. In 2000, the oligomer associated with cytotoxicity. In 2001, ex vivo amyloid fibers studied by cryo electronic microscopy. 2002 or 22, discovery of the structure of the insulin protofilament polyamyloid. 2005, poly-Q amyloid fibril model structure of the cross beta spine of amyloid fibrils. 2006, quaternary AB beta 40 structure helical twisted year. 2030, AB nanotube. 2016, structure of alpha synuclein fibrils, who is Parkinson disease. And 2017, cryo-electroscopy of in situ poly-Q inclusion structure of tau fibers. Key milestones in the history of amyloidosis. What is the physical nature of amyloid? Amyloid protein adopt a beta sheet configuration where the protein strand extended segment align side by side, connected by hydrogen bond between the NH and CO groups of adjacent residue. This arrangement forms anti-parallel beta sheet. The strands go in opposite direction. Characteristic orientation: the beta strands are perpendicular to the fibril axis, creating a repeating pattern called cross beta, first observed in 1968 by X diffraction here. And the structural parameters, distance, or we are going to see here, distance here by 4.7 angstrom between adjacent strands corresponding to hydrogen bonds. Distance of 10 or 8 to 11 angstrom between superimposed beta sheet. Hydrophobic and van der Waals interactions. Then, a proposed beta helix structure of amyloid fibers form showing aligned beta strands and the nanotube viewed from above, the fiber axis in the y-axis. And here, where this picture showed the electronic microscopy electronic showed of amyloid fibers. The characteristic optical properties of amyloid fibers stand with Congo red result from the particular binding of the dye to the fold beta sheet. This molecular organization of the dye results in deflection of polarized light with simultaneous extinction of the red component of the light spectrum, leading to yellow-green birefringence. Diagnostic test for the presence of amyloid in tissues. Several transformations of this protein form an enfolded form to a nucleus and the secondary, tertiary from a finally and definitive quaternary, which is insoluble form. The thermodynamic equilibrium towards the aggregate phase in the nucleation polymerization model describes how amyloid protein pass from the soluble state to the fibrillary state. The key steps are as follows: nucleation phase, growth phase, and stationary phase. The first one, nucleation, show initial phase, the soluble monomers assembled into small and stable aggregates called nuclei. This phase is thermodynamically unfavorable because it requires overcoming an energy barrier. Critical nucleus once formed, this nucleus becomes a stable seat for the addition of new monomers. And the polymerization, it's a rapid elongation phase. Monomers are rapidly added to the course, forming elongated fibrils. This stage is exergonic and thermodynamically favorable. Prolongation fibrils can fragment and serve as new nuclei, accelerating aggregation. Equilibrium, protein concentration, high concentration favor nucleation and aggregation. The final phase is stationary phase. Once the majority of monomers are integrated into the fibrils, the system reaches a dynamic equilibrium between soluble and aggregate forms. These fibers are correspond to 90% and polysaccharidic molecule 10% component of complement P, also known as AP, serum albumin protein, glycosaminoglycan, proteoglycan, heparan sulfate proteoglycan, calcium phosphate, fibronectin type 4 collagen, laminin, antectin, histone fragment. All these molecules have been shown to accelerate fiber formation in vitro. They form a real glue to bind the amyloid proteins and form an insoluble fiber. During folding, as the number of favorable interactions increases, the range of possible conformations decreases. Once the transition state configuration has been reached, the folding reaction inevitably proceeds toward the native conformation. This is therefore an energy landscape thought which proteins can navigate during the following reaction here, intramolecular interaction here, and intermolecular interaction here, and energy. Since the number of possible conformation decreases as folding approaches the native state. We are going to see what is the clearance process of this amyloid fiber. This schema described by Wilson presented the suggest that chaperone-mediated extracellular chaperone play an important regulatory role in the formation and elimination of amyloid in the body. A model is presented which proposes that under normal conditions, the extracellular chaperone stabilize the poorly folded extracellular proteins by binding to them and then guide them towards specific extracellular receptors for their absorption and subsequent degradation. For example, chaperone extracellular and their receptors could be essential component of high quality control system to protect the body from dangerously hydrophobic protein peptide. However, it also seems possible that in the presence of high molar excess of misfolded protein, as may occur in case of disease, the limited quantities of extracellular chaperone available can actually exacerbate the pathology. New advances in understanding the mechanism that control the folding of extracellular protein should lead to the identification of new strategies for effective therapies. Ubiquitination normally marks misfolded protein for degradation by the proteasome. Disruption of this pathway leads to the accumulation of abnormal protein, favoring their aggregation into amyloid. We are going to see what are the factors favoring fibrinogenesis. The passage of a folded protein into an expanded form, see amyloid fiber. This fibrinogenesis has the factors promoting, describing in vivo and in vitro. The first one, in vivo, ubiquitination normally marks misfolded proteins for degradation by the proteasome. Dysfunction of this pathway leads to accumulation of abnormal proteins, favoring their aggregation into amyloid. Then amino acid sequence, then impaired autophagy. Autophagy blocked amyloid aggregates can interfere with autophagy by uh, uh, by another cellular degradation system, exacerbating the accumulation of toxic protein in addition to the chaperone machinery, which assists in the correct folding of protein, is often overwhelmed by the excess of abnormal protein, reducing its effectiveness in preventing aggregation. The fourth one is oxidative stress to the proteasome. Amyloid oligomers can directly inhibit proteasome activity, exacerbating the accumulation of misfolded protein. Physical stress like mechanical stress, shear pressure, and air-liquid interfaces disrupt the solubility balance of protein and accelerating aggregation. Genetic mutation after conformational stability, example mutation in the CDR1 and FR3 regions of immunoglobulin light chains. In factors in vitro, protein high peptide concentration shifts the thermodynamic equilibrium towards the aggregated phase, nucleation and polymerization model. Acidic pH promotes partial protein folding and exposure of aggregogenic regions. High temperature increases molecular kinetic energy, facilitating interchain interaction, and agitation in molecular interaction like metal ion, zinc, and copper catalyze aggregation via electrostatic bridges. Membrane lipids serve as nucleation surfaces for fibrillar assembly. There are factors contributing to amyloidogenic protein aggregation are here in this schema. Environmental and cellular factors, protein-related factors, systemic and general factors, and physical and chemical mechanisms. The classification of amyloids. There are about 43 types of amyloid protein caused by folding different protein, and the type of protein and where it accumulates determines the type of amyloidosis. The ISA Nomenclature Committee met at the 19th International Symposium of Amyloidosis in Rochester on last 27 May on 2024, and publish, and this committee published in Amyloid, the Journal of Protein Folding Disorders. Every year, this group reviews the development of this table, discovery of new proteins, of new pathologies generated by these poorly linked proteins, and a reflection on the possible therapeutic for the eradication or stopping of the process. This nomenclature table is divided into 5 columns. The first column designs by the first letter designs A. Here A is the amyloid substance, following the A by the designation of abbreviation precursor of the fibrillar protein. The second column is the complete nomination of the protein. The third one designates if this protein is in large S, it means systemic, or in large L, means localized disease. The fourth column designates whether the amyloid protein is in large A acquired, or in large H hereditary, or innate. And the last column indicate that the depositing organ of predilection of this amyloid protein.